Okay, we've been talking about electrochemistry, and last time we got into sort of non-standard conditions of the Nernst equation. And again, we have E is equal to E naught of the cell minus RT NF natural log of Q. Again, this would be sort of under non-standard conditions. Remember, sort of standard conditions means basically 1 molar and 1 atmosphere. Again, those are the main two ones. If they are not in those situations, 1 molar, 1 atmosphere, then you do want to use obviously the Nernst equation. This is, as we talked about, our cathode minus our anode. R is our normal R 8.314 version. N is our moles of electrons, and F is our Faraday's constant, 96,500 joules per volt per mole. Q is our normal reaction quotient, which is the products over the reactants, obviously using the coefficients if necessary. Remember that if you get to equilibrium, you could kind of derive the other equation that we sort of saw, which was at equilibrium, E would equal 0 and Q would equal K. That again would give you Z is 0 is equal to E of the cell minus RT NF natural log of K. Again, basically adding this entire thing to the other side gives you our other equation there, which is RT NF natural log of K. So obviously involving the equilibrium constant or something to do with equilibrium, that would probably be the one to go with. Non-standard conditions, obviously that would be to go with. If it's standard conditions, all you want is to cell voltage like normal, you could roll with our cathode minus our anode in this case. We also saw delta G is equal to minus NFE. And in this case, remember that if we do have a positive voltage, that negative there will turn our delta G into a negative number, which should give us a spontaneous reaction. If we have a negative cell voltage, that negative and this negative here will turn our delta G into a positive, which means it will be non-spontaneous. And as we talked about, all three of those things, kind of the E of the cell, the delta G, and the K value, they all should really agree with each other. Again, if you have a positive E, you should have a negative G, and you should have a large value of K, as you mainly should have products. And vice versa, if you have a negative E, you should have a positive G, which means the reaction is non-spontaneous. And because of that, you will mainly have reactants, which means you should have a small value of K. Any questions on any of that there? Okay. Then I think we left off on this one here, so why don't you give it a go? Forget the balancing part, just do the E and the K part of it. Don't worry too much about it. Then we can see this guy's going from +2 to +3, becoming more positive in this case. So this guy's going through oxidation, which would mean that is my anode. If you're curious here, that's a -2, that's like a 10, that's like a 2.5 for that guy right there. And on this side, it's a -2, 6. It's like a +2. So this guy's going from 2.5 to 2, moving in the negative direction, not by a lot, but it is getting reduced in that case, which would be our cathode. So if we wanted to balance it, we do need a couple of electrons here. So we would have to multiply this by 2. That would put some 2's there. By the way, there would be a 2 there as well. And it should be balanced up as well. All right, so our E of our cell here going to be our cathode minus our anode. Once again, I'm going to subtract, so I'm not going to change any signs. As we talked about a number of times up to this point, if you did change the sign, then you should add and not subtract. So here my cathode is 0.17 minus 0.5 volts in this case. And that's going to get me a 0.67 volts, right? So we have a positive voltage, which means at this point we should know we should have a negative delta G, and that should mean we should have a spontaneous reaction that should be heading to products, and that should give us a lot more products than reactants. So we should end up with perhaps a big value of K here. So our E of our cell there, and the one that involves K, RT, NF, natural log of K. Remember, no negative on this guy. So our temperature here, even though it's not given, we'll just assume it's 298. There, it's probably a safe bet. We'll put our numbers in, and I'll go up high here so you can maybe see it. We'll go 8.314 joules per Kelvin per mole, 298. Our moles here are 2. Remember, we want just the moles transferred basically. And our 96,500 joules per volt per mole, and our natural log of K. So that's going to equal 0.67. So cleaning up kind of here, we got 8.314 times 298 divided by 2 and divided by 96,500. That's going to give us, if we kind of clean up that section there, 0.012837. Natural log of K equals 0.67 volts. Obviously, we're going to divide that now to the other side. 0.67 divided by that. That's going to get us here 52.1922 equals natural log of K. Going to E both sides. Hope for the best. And we'll get 4.6 times 10 to the 22. Again, I didn't round anything. I just took the whole number. So if you round it, you might get a slightly different front part. But the back part there should be okay, the 22 and stuff like that. Questions on that there? Okay, so obviously we have a few different equations, non-standard conditions, equilibrium, obviously equations we can relate it to our E of our cell. The next thing we're going to talk about are batteries, just a little bit. And really for batteries, you just need to kind of know in general, how they're similar to a traditional galvanic cell, and maybe how they're a little bit different. You're not going to be asked to write any specific battery sort of reactions or anything like that. So batteries are galvanic cells, or a series of galvanic cells that are used as a direct electrical current that has a constant voltage. They're self-contained. They don't have, the need for a salt bridge like a traditional one where you got a couple of beakers sloshing around, right? So obviously that would be very hard to put into your electronic devices, right? And everything's sloshing around with a salt bridge. But it's really sort of the same sort of function as a galvanic cell. And there's different types of batteries. Just going to kind of look at a few different ones here. And here I'm going to go with Duracell, looks like perhaps, right? And obviously a battery has a positive end, right, and a negative end like our galvanic cell, right? And this is a dry cell, sometimes referred to, as it doesn't have any fluid. It has more of a paste in the middle here, which is battery acid. The anode is a zinc can. And so here's our zinc with our anode, right? So our electrons would be flowing out through the wire in your device, right? In that fashion. And the cathode is a carbon rod that's immersed in this electrolyte solution. This sort of battery acid sort of functions like a salt bridge and allows everything to kind of flow. This type of battery will give you a basically voltage of 1.5 volts, regardless of what size it is. We got like D batteries or triple A's or A's, double A's, I guess, or the A's. But what we have here is our zinc going from 0 to +2, again, getting oxidized here. And over here, we have our Mn, which is going from +4. And on this side here, +3, getting reduced in this case. And here's our overall reaction that's happening here. And again, just the different sizes allow this reaction to continue for a longer period of time than a smaller one. Mercury batteries, on the other hand, are a little bit different, but also similar in a sense. They're used a lot in medicine, electronic devices. They're more expensive. They have sort of a zinc anode as well as our can here. And again, it is in a strongly alkaline electrolyte. So alkaline means basic, right? So something like potassium hydroxide here is used. And there's no change in this electrolyte composition during operations. So with this not really changing all that much, it hangs around a long time, allows this to really last for a long period of time, have a longer life without any degradation of our sort of salt bridge acting thing here. The overall reaction involves only solid things. That's also really good, as we'll talk a little bit about. It's really good for rechargeability and stuff like that, and long lasting is having solids in your overall reactions in terms of batteries. I get a little smaller sort of voltage happening in this case. Here again, we see our zinc going from 0 to +2, our mercury going from +2 here to 0, again, getting reduced in this case. Lead storage batteries, which are common in automobiles. There are actually 6 sort of cells put together. Each one gives you kind of like 2 volts for your 12-volt car battery typically. And that is enough, obviously, to sort of power everything on when you turn the key. Unless, of course, you're running late, then it will not turn on for you sometimes. But and get your other electrical sort of systems going as well. It's rechargeable. So if you've ever had a battery that died on you, right, they tell you to let it run for 20 minutes, right, to kind of charge it back up and stuff like that. And it's able to do that. We also have things like alternators, right, in cars like that, so we don't kind of drain the battery and stuff like that as we're driving it. Healthy batteries can have a density of 1.2. So here's sort of a cross section there of a traditional car battery. And again, they have some strong electrolyte solution in between, hence battery acids, something like sulfuric acid in there. We have our anode side, right, and our cathode side, which if you ever need to jump it, right, you got to put your cables on in the right ones. A lot of cars actually don't have batteries in the engine anymore, so a lot of them have them like in the back seat and the trunk and stuff, but they just kind of run the cabling to the engine in case you need to jump it and stuff like that. Here we see 0 here for our lead going to +2 being oxidized, and down here +4 for the lead going to +2, so getting reduced in this case. Once again, as I mentioned before, you can see a lot of solids here in our overall reaction. And as I mentioned before, that's really good for a battery's ability to sort of be recharged. This is a lithium solid state battery, and it has a carbon sort of material as its anode, and a cathode is a transition metal. And it actually has holes in it, so as the lithium gets oxidized, those lithium ions can sort of travel through this solid electrolyte. Lithium is a light metal, and that's why a lot of times these type of batteries were used in like tools and phones and things like that, because they're light and don't add extra weight. A fuel cell, which is not technically a traditional battery, but kind of works similar. In a fuel cell, this is a hydrogen fuel cell. You shoot in some hydrogen and oxygen in here. And again, in this case, we have hydrogen going from 0 to +1 being oxidized. Oxygen go from 0 to -2 being reduced in this case. And for a long time, people wanted to make cars in this type of fuel cell, again, because the only product there is water that was made. Obviously, we've now moved more to full electric or hybrids than sort of this guy, as obviously hydrogen is a little bit different to pump than a traditional sort of gasoline. So again, for batteries, you're not responsible for any of the specific reactions, but just similarities in terms of traditional galvanic cells and sort of batteries, how they function. Corrosion is another sort of idea here. And corrosion is returning metals to their natural state. A lot of steel production is made just to replace the rusted metals. Any metal that basically has an SRP, a standard reduction potential of less than oxygen, is susceptible to going through corrosion. And that's because if you have oxygen and it has a more positive standard reduction potential than a metal, when these two guys hook up, our oxygen is going to be our cathode and our metal will be our anode. And what's going to happen is this guy's going to go through oxidation, which is essentially what corrosion is. And that's going to cause the metal, obviously, to go through significant corrosion. Now, not all sort of corrosion is necessarily a bad thing. Some corrosion can actually create a layer of corrosion over the metal. And what it actually can do in certain cases is protect the metal that's underneath from further sort of corrosion and sort of deterioration. Aluminum is an example of that. Aluminum will form this sort of layer that will prevent further corrosion of the metal that's underneath. The problem, though, for example, with iron is it will do the same thing, but iron will not basically stay on. So as it corrodes and goes through corrosion and it creates this layer, that rust falls off basically. And when it falls off, it exposes new metal to further corrosion till eventually it just kind of corrodes all the way through. You put your finger through it and stuff like that. Copper forms this external layer, this sort of patina, which is expensive sometimes, right? And that's really just corrosion. Silver will tarnish as well, silver sulfide. Gold with an SRP value of 1.5 is actually larger than oxygen. So when gold, for example, gets together with oxygen, because the SRP for gold is actually more positive, gold actually acts as the cathode in that situation, and the anode would be over there at the oxygen, and that prevents gold from going through any type of really corrosion or anything like that, which is why it's sometimes referred to as a noble metal, right? So we have some noble metals like noble gases, which are chemically inert, and gold being one of those. As we talked about with iron, rust will occur. It actually occurs in a kind of couple of step process, but really all you need is a little bit of moisture, some iron, and some oxygen, and you're good to go for rust. Iron will actually oxidize iron too, and then as those electrons go down, it will further oxidize itself there to iron 3 and will form iron 3 oxide, which is basically what rust is as a result of this. And that's because steel has these ununiform sort of points on it, or pits. And what that does, it makes a nice grading brown for moisture to sort of sit. And obviously air has oxygen. And again, you now have all three combinations of what you need for rust basically to occur. And rust will start to occur again as this falls off. It exposes more and more of the fresh metal to this overall process. You also get a bigger sort of indentation where moisture can sit. And obviously that eventually will cost you a lot of money to replace your iron in this case. Now, there are a few ways you could prevent corrosion. One way is coating, so you could paint it, or metal plating. They sell Rust-Oleum paint for the name, I'm imagining, to prevent the metal from rusting. You could also plate something like chromium and tin, or you could do some galvanizing. And what that essentially will do again is create this coating that will protect the metal that's underneath it. Because when we coat the metal with zinc versus, say, iron, iron is now more positive than zinc, so iron becomes the cathode and zinc becomes the anode. So all the sufficient oxidation will occur on the zinc coating rather than the metal that's underneath it, and thus protecting the iron, which is what you want to kind of do. And that's why it's sometimes referred to as a sacrificial coating when you do that. You could also do some alloying, which is add some other atoms to metal, like stainless steel has chromium and nickel, and by doing so, it changes its standard reduction potential to something closer to a noble metal, and again, it prevents it from basically going through corrosion. Cathodic protection is another way you could kind of prevent sort of corrosion occurring. And for example, if you take magnesium connected by a wire to a pipeline or a tank, if you buried it underground, for example, a lot of moisture, and that's going to cause obviously corrosion that could occur. But what happens when you hook up that magnesium is a better reducing agent. And if you're a good reducing agent, that means you get oxidized. And all the oxidation again is going to happen over here at the magnesium. And in this case, this would be more the cathode in this situation. Again, it's going to prevent the oxidation of your iron sort of tank that you sunk in the ground. Titanium is used in ship hulls to sort of prevent that from happening. Here's a much prettier picture of that. But again, all the oxidation is going to occur over here. So you're not digging up your tank every 2 weeks as it starts to corrode and stuff like that. Any question on corrosion? So corrosion, you know what it is, maybe a couple ways to prevent it. Yeah, it's a good thing now. All right, the last thing we're going to talk about is electrolysis. And electrolysis is the process where we apply basically an external sort of energy, electrical current, for example, to cause a non-spontaneous reaction to occur. So for example, if we took something like sodium chloride and we ran an electrical current through it, we can actually get sodium chloride basically to go back into its natural elements, if you will. We could get some sodium liquid coming out, and we could get some chlorine gas that's going to come out as well. You basically break it apart into its elements, do a little balancing like a good chemistry place here. Now, when we do this, it is actually a different sort of process that's happening than what you might think. So what I mean by that is if we were doing I'm going to make sodium chloride in this direction, we have the sodium going from 0 to +1 and the chlorine going from 0 to -1. In this case, the sodium is being oxidized and it would be our anode. And this guy is getting reduced, which would be our cathode. But when we are actually going in the opposite direction, running electrolysis here, we're actually starting with +1 on this side and -1, and these guys are 0, which means when we're looking at this in the kind of reverse direction, the sodium's going from +1 to 0. It is actually becoming more negative, and the sodium in this case is actually being reduced, and that is our cathode. While the chloride is going from -1 to 0, which means it's becoming more positive, and the chloride in this case is actually being oxidized, and it is our anode. And that's what you see here in this. It is actually our chloride, which is our anode in an electrolysis cell, because we are taking it from, again, -1 to 0, becoming more positive in this case. It's going to release those electrons. Those electrons are going to come over here to our reduction side there and reduce our sodium ions that are present, and going to make, again, basically something going from +1 to 0 in this case. So when you're thinking about electrolysis, sometimes people always get it backwards because they think about sort of making something like the ionic compound and they think about what's being oxidized and reduced. But because we're kind of running that reaction backwards, your anode in a traditional sense now becomes your cathode, and your cathode becomes your anode. Any questions on that there? Now, water is another example of that. And again, when we make water, if you will, put a 2 there, maybe a 2 there. When we make water, we're going from 0, 0, and then again, +1 and -2. So in the process of sort of making water, hydrogen here is going from 0 to +1. It is being oxidized. Oxygen is going from 0 to -2. It is being reduced, which means, again, our anode would be our hydrogen in a traditional sense, and our cathode here would be our oxygen that's getting reduced. When we're doing electrolysis, which means we could run just basically an electrical current across water and break it apart into hydrogen gas and oxygen gas, we are going in the opposite direction. Again, +1 and -2 on this side, 0 and 0. So here the hydrogen is getting reduced and is our cathode. Our oxygen here is being oxidized and is our anode. By the way, you could do this with just like a 9-volt battery and some electrodes and a little bit of acidic water to help it out. By doing acidic water, and you have an extra supply of hydrogen ions kind of flying around in there, and that helps kind of reduce those guys to hydrogen gas. By the way, when you are talking about the electrolysis of water, especially in books and stuff like that, they frankly don't a lot of times just straight up come and say, hey, we're doing the electrolysis of water. They basically will say, hey, you ran an electrolysis cell with something like sulfuric acid or something with some type of acid. And that's usually a key that they're talking about the electrolysis of water. And these would be the half reactions that you would want to use. So again, for books, sometimes they don't straight up just say, hey, we're doing electrolysis of water. So if you see something that really doesn't say what it's doing, but it mentions something about dilute acid or strong acid, like sulfuric acid, then you're probably doing the electrolysis of water. Now, when we do that, as I say, you can run electrical current. You will see basically the water start to bubble out in the hydrogen gas and oxygen gas. And in this empty spot here, right, we're going to collect some hydrogen gas, and over here some oxygen gas. And why does it look like I have more hydrogen than oxygen in this case? That is because the formula is H2O, right? Twice the amount of hydrogen as you do oxygen. So you typically will collect twice the amount of hydrogen gas than you do oxygen gas when you're collecting it. Any questions on that there? So when we do these electrolysis problems, there's sort of a common sort of pathway in terms of doing it. A lot of times they will give you the current in an amperage, and an amperage is a coulomb per second is the relationship. And a lot of times they'll give you the time. And because an amperage is in a coulomb per second, you oftentimes want to get your time into seconds as well so that those guys will kind of cancel out. And by using basically the time and the current, you could take your seconds and times it by your coulomb per second, which is your amperage. The seconds will cancel. And this will give you a coulomb, which is a unit of electrical charge. And at that point, what you could use is our friend Faraday's number right there, or constant, basically. You could use that to go from coulombs of charge into moles of electrons. And it's at this point you will essentially get moles of electrons. And this is where the half reactions come into play, your anode half reaction and your cathode half reaction. So, let's just say, you had a relationship of a metal and, maybe had the metal and it was like 2 electrons or something like that, and one of the metal. So what you could do at this point is actually like a stoichiometry sort of relationship. You could do like 1 mole of the metal gives me 2 moles of electrons. And you can use those moles of electrons to, for example, go to the moles of the metal. Or you could also do with the non-metal, for example, if we're talking about kind of like an ionic compound, you could do the moles of the non-metal to how many electrons you have in the balance half reaction. What that will essentially give you is moles of either, for example, a metal or a non-metal. And then you might be asked one of two things at the end. If you might be asked maybe how many grams you would produce. And obviously, if I have moles and I want to go to grams, that is the molar mass, right? From the periodic table is going to allow you to do that conversion. Now, as we were just talking about with sodium chloride, we actually produce chlorine gas, and even with hydrogen and oxygen gas that was produced from water, a lot of times in electrolysis sort of cells, you will produce a gas. So sometimes they're not necessarily interested in how many grams of that gas you would produce, but they may be interested in the volume of the gas. And that usually means we will throw back old school here, a little PV equals nRT action. Yeah. And sometimes you will have to use the ideal gas law to figure out the volume. A reminder, pressure needs to be in atmospheres. Volume needs to be in liters. Moles should be moles. Temperature should be Kelvin. And also a good reminder, since we've been using a different R for a lot of problems, this is the gas constant R, the 0.08206 version of it. So sometimes at the end of these calculations, you may have to use ideal gas law to figure out a volume rather than grams, or if you want grams, molar mass at the end there. Question on that there. There's also sort of variation on these type of problems where maybe they'll tell you how many grams you produced or how much volume of a gas you produce, and you have to work backwards to figure out maybe how long the cell ran for or what the amperage was on the cell. So sometimes you kind of go forward or backwards in these kind of calculations. So let's take a look at one together. We'll come back to this one here. Let's see this one here. And let's say we want to know how much calcium would be produced in an electrolysis cell of calcium chloride if a current of 0.452 amperage is passed through the cell for 1.5 hours. So in this situation, what we have to remember is we are going in this direction to make calcium and chlorine gas in this case. And basically the calcium is going from +2 and the chloride is -1 to 0 and 0. So in this particular case, the calcium is going from +2 to 0. It is being reduced. And this guy, again, is getting oxidized, which means if we take a look at our reduction, we should have calcium with a +2. +2 electrons gives us molten calcium here. Go solid. And for our other one, it is 2 chlorides making Cl2 plus 2 electrons happening here. Again, our cathode and our anode here. Any questions on that there? So these two half reactions are important because, again, in our calculation, that's what's going to allow us to figure out the moles of what we need. So to get there, though, we will start with our amperage, which, again, 0.452 amps is the same as 0.452 coulombs per second. And because that is coulombs per second, I am going to convert my hours into seconds. Once again, just to make sure everybody's in the same units. So I'll take 1.5 hours. And 1 hour, there are 3,600 seconds. And that's going to get me 1.5 times, not subtract, times 3,500. 3,600, it's kind of like 35. Gives us 5,400 seconds. We now can use the current of the cell, and we can go 0.452 coulombs per second. They're going to cancel, and that's going to get us here 2440.8 coulombs. So basically, we're taking our time we ran the cell and we're times it by our amperage, and that's going to give us coulombs of charge. This is where we can use Faraday's constant to convert it into moles of electrons. So we'll take our coulomb of charge, and we're going to use Faraday's constant at this point, 96,500 coulombs per mole of electrons. And that's going to get us here, divided by 96.5, 0.025 moles of electron. At this point, we can now really figure out how much of each of these guys we're going to basically be producing. In the case of the question, it was interested in calcium. So from the half reaction here, we could see that for every 1 mole of calcium, we get 2 moles of electrons. It's just like stoichiometry, basically, the mole-to-mole relationship between electrons and what you're interested in from the balanced half reaction. So if I do that for calcium, that's going to give me here 2 moles of electrons, and 1 mole of calcium will tell me I will produce here 0.0126 moles of calcium. In this case, if I'm looking for grams, I could go to the periodic table and use the molar mass of calcium, which is 4008 grams per mole. And if I times that by 4008, I am going to produce a whopping 0.51 grams of calcium in this particular case. Any questions on that there? If by some chance I was interested in chlorine, I could do the same thing. I could actually pick it up right here. And if we wanted to for chlorine, go 0.025 moles of electrons. For chlorine, it is also a 1-to-2 relationship from the equation. And we would have 2 moles of electrons, 1 mole of chlorine. And in this case, we actually will get a similar number here in terms of our moles of chlorine. And at this point, if, for example, I was given maybe pressure or temperature, I could use the ideal gas law to figure out the volume I would collect. Or if for some reason I wanted grams, I could use the molar mass of chlorine, which would be 3545 times 2. That'd be 90 grams per mole chlorine. If I didn't have that other information to kind of use the ideal gas law. And in this case, we would actually produce 0.89 grams of chlorine gas in this case. Any questions on that one there? Like I said, kind of a similar calculation for these. Can work your way backwards. Like I said, sometimes they may say, hey, you produce 0.5 grams of calcium in this cell. You know, how long did you run it for if it was at this amperage, or how much amperage you did if you ran it for a certain amount of time. All right, so why don't you try one here? Why don't you try this one, which is actually a current of 1.26 amperage. It's run through an electrolysis cell that contains sulfuric acid for 7.44 hours, right to half reactions, and figure out the volume of the gas generated. So this is also what I was talking about earlier. There is absolutely no mention in this problem of water. Yeah, but this is the electrolysis of water. Again, the key right there is you're running it through a sulfuric acid solution. So again, that's very, very common. By the way, STP means standard temperature and pressure. That's a temperature of 273 Kelvin, right? And a pressure of 1 atmosphere. So we're looking for the volume of hydrogen gas and oxygen gas run 1.26 amperage for 7.44 hours, right? Here are the half reactions, so you can just pick it up from there. 7.44 hours at STP. Again, 273 Kelvin and 1 atmosphere pressure. We want to know the volume of oxygen gas and the volume of hydrogen gas collected in this case. So give it a go, see what you come up with. Okay, let's take a look since we're getting to the end here. So we're looking for the volume of basically the hydrogen gas and oxygen gas in this case. The beginning part of the calculation is pretty similar to what we did previously. We need to basically get it to moles of electrons so that we could then get into the half reactions, basically get our moles of our hydrogen gas and oxygen gas. So I'm going to convert my time here into seconds. And that again is an hour is 3,600 seconds. I'll go on the other side of that, I guess. 7.44 times 3,600. Going to give me 26,784 seconds in this case. I need to do that because this guy right here is basically 1.26 coulombs per second. That is what an amperage equals. And again, that's what's going to get us into our coulomb of charge here for this cell. So 26,784 seconds. We're now going to times it by the current here of 1.26 coulombs per second. Those guys are going to cancel. And that will get us here. Looks like 33747.84 coulombs. This is where we're going to use Faraday's constant to get us into moles of electrons. So we're going to divide by it. And that will get us to our moles of electrons. And in this case here, it looks like a 0.3, we'll call it 50 moles of electrons. First off, any question on the calculation? That again is necessary so that we can then basically use our half reactions to get to the moles of each of the gases in this case. So we'll start with the top one here. From the top one, we can see that for every 1 mole of O2, we get 4 moles of electrons. So again, just like stoichiometry, coefficients is what we're doing. So for our moles of O2 in this case, we'll go with our moles of electrons. Using our balanced half reactions here, 4 moles of electrons gives us 1 mole of O2. And that's going to give us our moles of O2, which essentially would be 0.0874 moles of O2. We'll do the same thing here for our moles of hydrogen, which we need to use the other half reaction. There is actually a 4 over here. If you multiply that 4 across, that will essentially give you 4 moles of electrons equals 2 moles of hydrogen. That's also the same as 2 moles of electron equals 1 mole of hydrogen. You could use either one. It doesn't really matter. You sound the same when you do the math. So we'll go 0.35 moles of electrons. I'm just going to use the numbers from the equation after we multiply. So that's going to give me 4 moles of electrons, 2 moles of hydrogen, and that will get me here 0.3. Actually, let's use that number there. Gets me 2 divided by 4, 0.175 moles of hydrogen. Any questions so far? At this point, I really have everything I need for the ideal gas law. So taking the ideal gas law, PV equals nRT, I'm going to solve for V in this case. So the V of the oxygen would be nRT divided by P. Putting in my moles for oxygen, 0.0874 moles. My gas constant, 0.08206 liters atmosphere Kelvin mole. If you like 0.0821, that's perfectly fine too. 273, right, is what STP stands for. and 1 atmosphere is what STP stands for in terms of the pressure. That's going to get me here for my oxygen. About 1.96 liters of oxygen gas was collected. Questions on that one there. We're basically just going to rinse and repeat here with the hydrogen. It's going to go into the same formula. Again, an nRT divided by P. We do want to make sure we use our hydrogen moles in this case. So 0.175 moles, our same gas constant, our same temperature, and our same pressure at this point, which is 1 atmosphere. Again, putting it in there, everything's going to cancel out, but liters, moles cancel, Kelvin cancel, atmospheres cancel, leaves us liters. So 0.175 times 0.08206 times 273, a 3.92 liters of hydrogen gas was collected. And dare I say that is 2 times the amount, right, as we had of oxygen like we talked about. First off, any questions on that there? Could I have solved this another way? The answer is yes. If you remember, because this is at STP, maybe you remember that 1 mole of any gas at STP equals 22.414 liters. So if you remembered that, you could have, for example, took the moles of hydrogen and just did 0.175 moles of hydrogen. 22.414 liters is a mole of hydrogen. Moles will cancel. You could bypass the ideal gas law in this case. Remember that you could only use that conversion if it is at STP. If it's not at STP, you should never use that conversion. So that's always specifically for STP. Otherwise, you can put it into the ideal gas law like we did there. Question on electrolysis type problems. All right, that wraps up this chapter.